Hello and welcome back to Materials Conceptual Study. In today's lesson, we will explore one of the most important fundamental concepts in crystallography, the atomic packing factor, and how these apply to the most common crystal structures like simple cubic, body-centered cubic, and face-centered cubic. By the end of this video, you will understand these structures and how their atoms are packed and the derivations behind their packing efficiencies. First, let's understand the atomic packing factor. It is actually the fraction of space occupied by atoms, assuming that the atoms are hard spheres. So, it is a measure of how efficiently atoms occupy space in a crystal lattice and used to calculate how much portion of the unit cell is occupied by the bravais lattices in crystal structures. For example, the atomic packing factor of simple cubic crystal structure is 0.52, which means only 52% of the unit cell volume is occupied by the atoms and the rest of space is empty in one unit cell of simple cubic crystal structure. Similarly, BCC unit cells have a packing factor of 0.68, which means only 68% of the unit cell volume is occupied by the atoms and the rest of the space is empty. The simple cubic and body centered cubic crystal structures are relatively open, but the atomic packing factor of the FCC unit cell is 0.74, which is the most efficient packing possible. It is also possible to have a hexagonal structure that has the same packing efficiency as the FCC structure. This structure is known as the hexagonal closed pack structure. Mathematically, atomic packing factor is defined as the volume of atoms in a unit cell divided by total unit cell volume. To calculate atomic packing factor, we required three things. Firstly, the number of atoms per unit cell, which is different for each unit cell. For example, simple cubic crystal system has only one atom per unit cell, but body centered cubic crystal structure has two atoms per unit cell. We will shortly after show you how do we calculate the number of atoms per unit cell. Second thing which is required is the volume of each atom, which depends on the atomic radius. And the third thing which is required to calculate the atomic packing factor is the volume of the unit cell, which is also different for each crystal system. Now consider the example of simple cubic crystal system and calculate its atomic packing factor. For this, we need to calculate the number of atoms per unit cell. In this system, atoms are located at the corners of the cube. Each corner atom is actually shared by 8 unit cells, so it contributes only 1/8 of its volume to the unit cell. As there are 8 corners of a unit cell, so multiply it by 8, we will get 1, which is the number of atoms per unit cell in a simple cubic system. So, number of atoms in simple cubic system is only 1. To calculate volume of each atom, we need to know the volume of a sphere. As atoms are considered to be a hard sphere, so its volume is equal to 4 by 3 pi r cube. So the volume of each atom will be equal to 4 by 3 pi r cube, where r is the radius of the atom. The last step is to calculate the volume of the unit cell. The volume of a cube is actually equal to the volume of the unit cell, which can be calculated by multiplying length, width and height of the unit cell. In a simple cubic crystal system, all the three dimensions are equal, which is equal to 2r, where r is the radius of the atom. So the volume of the unit cell for simple cubic crystal system is 8r cube. By putting all the values to the formula, we will get 0.52, which is the atomic packing factor of simple cubic crystal system. It shows that only 52% of the volume is occupied by atoms, making simple cubic crystal system the least efficient packing structure. Thank you for watching. I hope this video helped you to understand atomic packing factor. Don't forget to like, share and subscribe to Materials Concept Study.